Now let me get into multiple linear regression without wasting time, because that's a bigger concept. Here is where you have the real, what do you call, edge in the market. Very rarely you will see one input, one output. So that is why I haven't spent much time on that. Now let me load this data set called cars dataset, and let me show you that. So there are 81 observations, meaning you have 81 rows and you have 5 variables, 5 columns. And we want to predict miles per gallon, which is your output, based on all of these inputs. So how many inputs do we have? 4 inputs. Right? We have horsepower, we have volume, we have SP, and we have weight. I don't know what that SP means, and I've been training since years now, and I did not bother to find out what this SP is. Sorry. If any one of you all do some research, let me know what this SP is. Or WT stands for weight. Okay. Now, what is this Y? Continuous or discrete? Miles per gallon is continuous or discrete? Continuous. Why? If we can represent something in decimal format, it is continuous. So Y is continuous. Irrespective of what your input variables are, if I have multiple inputs and if Y is continuous, what regression technique would we use? Multiple linear regression. We go with multiple linear regression. So, all right, let us move on now. As part of the first step, you know for a fact what we have to do. Let me attach this so that I need not refer to column in a different way. First, we need to do elementary data analysis. Elementary data analysis is all about doing the summary, etc. Now, people, I forgot this, and I request you all to just remind me on where do you use this summary, where do you use this minimum option and maximum option once we build the prediction model. Just let me know about that. Okay, remind me, please. Otherwise, you'll miss out on an important option. I have very bad memory. Okay, so now if I were to do scatter diagram, I need to do scatter diagram between miles per gallon and horsepower, miles per gallon and volume, miles per gallon and SP, miles per gallon and weight. But do I need to run 4 lines of code? No, I would just do pairs of cars. There you go. Now, can you all tell me what is the correlation between uh, horsepower and SP? What is the correlation between these two? I mean, if I draw a diagonal like that, above and below, it will be a mirror image. Don't worry about that. Look into above triangle or below triangle, lower triangle, up or upper triangle. What is the correlation between these two? It's a positive correlation. It's a positive correlation. What is the correlation between volume and weight? Here is volume, here is weight. It's a positive correlation. Now a follow-up question. Should we have the correlation between output variable and inputs, or should there be a correlation between different input values? Listen to me very, very carefully. Very, very carefully. Always a strong correlation between output variable and input variable means the input variable is going to influence your output variable. That means if at all output is miles per gallon, right? If at all assume that there is a strong correlation between miles per gallon and horsepower, what does that mean? That means that horsepower is going to help you predict miles per gallon. If there is no correlation between miles per gallon and horsepower assume, that means this variable horsepower is least important input for me in predicting this output. Clear? Why should we look into the correlation? We need to look into the correlation because if the correlation is not there between output variable and input variable, that means the input variable is least important for you. Remove it from your analysis. Getting me? Be quick in saying yes or no. If no, I will repeat it. If yes, I will move on. Perfect. Now, if the correlation here, the correlation between miles per gallon and one input called horsepower seems to be negative. What does that mean? Negative correlation means as in how your horsepower value increases, your miles per gallon decreases. Simple. Negative correlation means as in how horsepower increases, miles per gallon decreases. What does your common sense say when it comes to vehicles, cars or bikes or whatever be your vehicle? What does your common sense say? As in how the power of the vehicle increases, mileage would decrease. So based on your common sense or subject matter expertise, this kind of a correlation seems to be correct. This makes sense. Absolutely, Sushant. This makes sense. So you need to evaluate all of these things. So do not think that you're just plotting, checking the correlation and moving on. There is a bigger essence. Okay, now second thing. If you see there, this is an input variable, this is also an input variable. There is a strong positive correlation between these two inputs. What does that mean? That means volume and weight are capturing similar kind of information. Volume and weight are capturing similar kind of information. And if two variables are capturing similar kind of information, then why do you want both? Why can't you have only one variable? Why do you want to make your analysis difficult by including another variable which is also capturing the similar kind of information which volume does? There is wealth of information that your scatter plot gives you. Probably if you spend some more time, I don't know, I think there is a cluster here, there is a cluster here, and there is another cluster there. There is a cluster here, there is a cluster here, and I believe there is a cluster here. Or maybe there are two clusters. Carefully analyzing your visualization will give you wealth of information. That is the reason why spend 60% of your time in exploratory data analysis, which includes your data visualization also. Do summary, describe the data, do summarize the data, aggregate the data, look into various permutations, combinations, then look into your dot plot, look into your box plot, look into your histogram, look into your scatter diagram. You will gain wealth of information. 60% of your analysis should be only spent on these. This is what will make you a real true data scientist. If you jump in to build your prediction model, it will go wrong 100%. Take my word on that. You build some model, you don't know what the data is, you don't know how the data is behaving, you don't know whether data is right or wrong, and then you have built a beautiful model. What is the use of that? It would not give you the business benefits. Remember, we are building prediction models to make our organizations profitable. You can also give false alarms. I mean, go and explore. People, data scientists in Italy were jailed, sentenced for 15 years because they've taken for granted in predicting the earthquake. Do a Google search. We are lucky we are in India. I mean, you guys are in US. You guys are a little lucky, right? People in India are also extremely lucky for that case. We know what happened with Chennai incident. If the same thing would have happened in European Union or some other country where rules were strict, people would have been behind bars by now, right? So please do not take it very easy. 60% of your time should be spent there. Okay, anyways. So now you know the importance of everything. Now we can also look into correlation coefficient values and determine on whether this image that you're seeing here or the scatter diagram in light with this. So we know for a fact using the scatter diagram that there is an extremely strong correlation between volume and weight. So if I look into volume and weight here, the correlation coefficient value is 0.99. What does that mean? There is an extremely strong correlation between these two inputs. And we know for a fact that there should not be very strong correlation between inputs. There can be a very good correlation between outputs and inputs, but not between inputs. All right. What would happen if there is a strong correlation between inputs? The problem is called as collinearity problem. If you have collinearity problem, that means if your inputs are correlated, then your prediction would be wrong. Prediction would be distorted. All right. So we will try to see on how to solve that problem. First of all, let us now build the model. I'm trying to use all these four inputs and I'm trying to predict miles per gallon. That is what I want to predict. Using this assignment operator, I'm assigning it to an object called model.car. Output is stored in this object called model.car. Let me do summary of model.car. There you go. How do we form an equation? How do we write an equation? Anyone? So what are we trying to predict? Miles per gallon is equal to, before that, output is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4. Why 4 x's? Because we have four inputs: volume, horsepower, SP and weight, and this intercept value is beta naught. So miles per gallon is equal to 30.6 minus 0.33 times of volume minus 0.2 times of horsepower plus 0.3 times of your SP plus 0.4 times of your weight. So the negative sign here says that as and how your volume increases, your miles per gallon decreases. Horsepower negative sign says that as and how your horsepower increases, your miles per gallon decreases. SP here says that positive value. As and how your SP increases, your miles per gallon increases. And weight here says that as and how your weight increases, miles per gallon or mileage increases. Is this true? What does your common sense say? Subject matter expertise, what does it say? If the weight of the vehicle increases, will the mileage also increase? What do you think? Anushri, Mamta? Decrease. So again, there is something wrong going on here. Keep all these things in a record. Take a notebook, record all these things. I mean, when you do in real life, just record all these findings in a place, right? Write down in a particular document. And here, this value seems to be significant, can be used in my prediction equation. This seems to be significant, this seems to be significant. Why is that so? Because the p-value is less than 0.05. I repeat, p-value less than 0.05 means p probability is less than 5%. Why for 5%? Because your management wants you to be 95% of the times correct. That means 5% of the times you might go wrong. 5% of the times you might go wrong means what? If the probability of you going wrong is less than 5%, then these values can be used in your prediction with confidence. Chance of you going wrong with the prediction is less. Or statistically speaking, these values are statistically significant if p-value is less than 0.05. Or another statistical statement is these values are significantly different than 0 if the p-value is less than 5%. Okay. Now what do we do with these two? Volume and weight. These two are not significant. So I'll try out something else. I will try to build a model only using volume because volume doesn't seem to be significant. So let me build it only using volume, linear regression model, and I've stored it in this object. So let me do a summary of that object. Okay, now here it seems to be significant. And if I do it only using weight, oh, if I use it only using weight, still it is significant. But if I do it using both volume and weight, nah, both of them are not significant. What does that mean? There is some collinearity problem or some interaction going on between volume and weight. I have double confirmed. I already know that there is a collinearity problem using what? Correlation coefficient using scatter diagram. I'm again double confirming it. Okay, so what to do with that, I'll discuss in just a moment from now. But when we build this model using all these inputs, we also have to look into the R-squared value, right? And here the R-squared value happens to be 0.77, which is very good. Which is very good by all standards. Even if R-squared value is 0.4, in real world, even if you see a p-value or R-squared value of 44% or 0.44, you'll jump with joy. Here the 77% or 0.77 means 77% of your variation in output variable y is explained using the inputs. 77% of variation in output is explained using inputs. Statistical explanation. You need to know statistical explanations anyways. So what is this adjusted R-square in that case? So let me tell you that. In reality, you need to look into both of these values. And if there is no huge difference, that means all is well. If there is a huge difference, that means either the inputs chosen are wrong or increase your sample size. If inputs chosen are wrong, what would you do? Choose some other inputs. Check with your subject matter expert. Or the third thing is check for data accuracy. Someone might have accidentally given you wrong data or purposefully done. You need to analyze the data. I mean, again, it's a notion okay, let me not get into that measurement system analysis and all that. Anyways, in brief, look into this concept. It's discussed in Six Sigma basically. Measurement system analysis, do an attribute agreement analysis if you have discrete data, and do gauge R&R if you have continuous data, even before you use the data. In mission critical projects such as nuclear power plant and wherever you're going to, wherever lives of humans are involved, right? These kind of measurement system analysis is used to check whether the measurement system in itself is reliable or not. Only if your measurement system is reliable, the data collected from this would be reliable. There are a bunch of other management techniques which you can use, All right. Uh, oh, that's one thing. One another thing is, if I keep on increasing the number of inputs, here we have 4 inputs, right? If I increase the 4 inputs to 40 inputs, your R squared value will increase irrespective of whether these 40 inputs are actually influencing your output or not. That means increase in inputs would increase your R squared value. Or from 4 inputs, if I reduce it to 1 input or 2 inputs, your R squared value will decrease irrespective of whether the inputs removed are actually relevant to your output or not. This kind of influence doesn't happen when it comes to adjusted R squared value. And from the overall p-value, look into F statistic p-value. Why am I getting 4 degrees of freedom here? Here, how many measurements do you have? 1, intercept value, 2, 3, 4, 5. So how many betas you have? Beta naught, beta 1, beta 2, beta 3, and beta 4. You have 5 measurements. So if you have 5 measurements, you'll have 5 minus 1 degrees of freedom. Hence you have 4. Why am I getting 76 here or here? How many observations do you have? 81 observations. So I have 81 observations. And how many calculations am I doing? 1, 2, 3, 4, 5 calculations. So 81 minus 1 is 76. Just in case you want to know how those values are getting calculated. I would say look into both, Smitish. Look into both. A huge difference is a problem. Yeah. If there is no huge difference, then there is no problem. Absolutely. Now this is the code. Don't ask me to explain this code, please. Go through it when you find free time. What this code actually does is, when I do this pairs, on one side of the panel you can see the correlation coefficient values, on another side you can see the scatter diagram, so that it'll become easier for you to correlate instantly. That's it. Nothing else, right? That code does. Okay. So there was that collinearity problem. What is collinearity problem? Anyone? We have discussed enough about collinearity problem. Now it should have been internalized by now. What is collinearity problem? If there is a correlation between various inputs, then that is collinearity problem. I repeat, Sushant. If there is a collinearity, if there is a correlation between inputs, then that's collinearity problem. Now, non-independent inputs, bookish answer. You cannot have inputs with absolutely zero influence. Absolutely independent inputs would never occur on this planet. There would be some dependency. Don't go by that term called independent. I am absolutely with you in that line, abbreviation and all that, but this is a very dicey term. In interviews, never ever say that we want independent inputs. Say that though theoretically they have to be independent, we can never ever get independent inputs, and there would never be zero correlation between inputs. That would never happen. There will be correlation between the inputs, whatever you do, except for principal components, principal component analysis. Yeah, Smitish, I'll just rectify that. If there is even moderate correlation between inputs, that's a problem, not just strong correlation. Mamta, what is that using the same data? Anyways, you can explain me in detail. I'll move on. So what we are trying to do here is we are also looking into something called as partial correlation matrix. So here there is correlation matrix which we have drawn, but here what happens is, though uh, take example of this value. This is what correlation between weight and volume. Though we are looking into the correlation between weight and volume, which is 0.99, there will be some influence of horsepower on this correlation. There would be some influence of SP on this correlation. There would be some influence of miles per gallon on this correlation. If you want pure correlation between these two, by excluding the dependency or the influence of the other variables, then we go with something called as partial correlation coefficient. It's subjective, Smitish, once again. What correlation value we can consider as a base for determining the collinearity? Subjective. In certain scenarios, even a weak correlation might have a collinearity problem. So it's all exploratory. You need to explore the data. See, for example, when we have explored here, we found that volume and weight are not coming up to be significant. So this is one way to confirm a collinearity problem. One way to confirm is actual correlation coefficient values. Another way to confirm is partial correlation coefficient. Another way to confirm is VIF value. So I'll tell you all that in a moment. So in order to come up with partial correlation coefficient value, you load this library, and this is the function. There you go. And let me also compare this with the correlation coefficient values. Okay. Now here it was 0.99 between volume and weight, but here it is 0.998. So it's slightly decreased. That means even if you exclude the dependency of the other variables on the correlation between volume and weight, it's not changing significantly. That means there is some collinearity problem. Again, you have confirmed on that, right? But how to deal with? I think it makes sense for me to bring in VAF here itself. Mm, okay, there is something called as VIF, variance inflation factor. If this value is greater than 10, that means there is collinearity problem. This is a formal way to assess the collinearity. So let me run this VIF. Okay, there is some package which is missing. Yeah, so car is a package um, which has to be installed and loaded before you do VIF. So again, I'm telling you, it's very exploratory. Look at this VIF value. Though the thumb rule says if the VIF value is greater than 10, there is a collinearity. All these four inputs have collinearity problem. Everything is greater than 10, right? But though everything is greater than 10, horsepower and SP were turning out to be significant. Volume and weight were not turning out to be significant in your regression output. So probably there is some problem with this or this. Now what to do? Delete either weight or volume, or try to transform the data. When I say transform the data, maybe you have to take log of weight, log of volume, and then try to regress and see whether you're getting the desired output or not. If log is not working, take exponential transformation, do reciprocal transformation, do a square root transformation, do a cube root transformation, or do a box cost transformation, do a Johnson transformation. And let me tell you this, if the client gives you 6 months, you can continue to work for 6 months in building the same model. You can perform umpteen number of operations on this. If the client gives you only 1 week, then you'll not do any transformation. Simply delete this or this and then run the model and give a model to the client. The more the time that you spend, better will be your model. Now, which one to delete? I would get to that in a moment. Obviously, you know for a fact that from this, I feel that VAF value is very high for weight, so we can probably delete this. But let us also double confirm before deleting anything, right? So before deleting any observation or any variable, first we need to check on whether you can delete one of these 81 entries. So notice clearly, if I delete this weight, I would get rid of how many rows? 81 rows, because we have 81 rows. This entire 81 rows for weight is gone. Instead, if I can somehow find out on whether any specific row can be deleted, and because of which can I get rid of this problem, that is another thing that you need to look at. Because if you delete a single row, how many values are you getting rid of? 1, 2, 3, 4, 5. However, if you delete the entire column weight, how many entries you're getting rid of? 81. Deleting each data point has to be done with caution because collecting the data is such a difficult task and costly affair. I didn't get you, Smitish. Mostly they asked to determine that. Means? Yeah. So normally you do not give a single proposal, right, to the client. You'd obviously say, hey, it depends. If you want an accuracy of greater than 60%, less than 70%, then the timelines would be 1 month. If you want accuracy of greater than 70, less than 75, then 2 months. As and how you keep increasing the accuracy, increase the timelines with to a great extent. 3 months. Greater than 95%, I would say give 1 year. Again, it depends on the industry that you're working with, so on and so. That you'll come to know. It depends on different companies. And the moment you guys become data scientists, probably I'll be getting in touch with you all to know how your organizations are working so that I can take some best practices from you all. All right. Now, uh, let me go to linear regression modeling. This is the prediction model equation, right? One more thing that I forgot, friends. Whenever you're predicting a value, it's represented using a hat. Otherwise, it's given. This is predicted value. This is the actual value. Whenever you have predicted values, it's hat. Whenever you have a predicted value of beta naught, it's beta naught hat. Okay. So line is the assumption. Whenever you build a model, it is not something that you have built a model, job done, wash your hands, go home. Even before you run that model, even before you finalize the model, you need to ensure that the model assumptions are satisfied. And line is a model assumption. L stands for linear, I for independent, N for normal, and E for equal variance. Linearity, you know how to find out linearity in the various parameters using scatter diagram. You can do that. Okay, Sushant has done that research. SP in previous example stands for top speed of the car. Thanks for that, Sushant. Okay, so that means these coefficient values should enter linearly into the equation. I can put a square here. It will become quadratic. But what I'm interested in is whether these coefficient values or parameters or estimates, are they entering linearly into the model? Of course, scatter diagram is the best bet for that. Second thing is assumptions about the errors. Errors. Error is what? Predicted value minus actual value. Your error should be independent and identically distributed. If you take average of all your errors, it should be 0. If you calculate the variance, it should be constant. And if the variance is constant, it is called as homoscedasticity. That means there's no problem. However, if there is no constant variance, it is a problem of heteroscedasticity. And one more thing is these errors should be independent of each other. Errors should be independent of each other. If they are not independent, then there's a problem called as autocorrelation problem. Guys, spend a lot of time on this slide and this recording. Go through at least 20 times if you do not understand. This is heart of your uh, entire data analytics. Okay, because majority of the times you will have continuous output and then you use linear regression. And assumptions about the predictors. Predictors are what? Inputs. They should be non-random, meaning you should have determined your historical data upfront. Non-random means historical data is decided upfront. You have the data with you. And measured without error, we are assuming that there is no data entry error, or the measurement system is reliable when you have collected the data of inputs. These inputs should be linearly independent of each other. If they are not independent of each other, there is a collinearity problem. Here we are discussing about independent inputs. Here we are discussing about independent error values. And finally, all of your observations should be equally reliable. So all the entries that you have should be equally reliable. It should not so happen that, hey, I'm giving you 81 rows. Out of these 40 rows, I'm 100% sure it's correct. Another 41 rows, I'm not so confident. Gone. Right? Each and every observation should be equally reliable. Okay. Now, let us try to solve this using the R code. There is something called as plot. Plot does variety of things. Plot in some sense will give you, in some scenarios, plot would give you box plot. Plot would give you, in some scenarios, a box plot. In some scenarios, it would give you a line plot. In some scenarios, or in regression scenarios, you'll get this. Look, let us look into this. This is the first entry. These are the residuals. Residuals or errors mean the same. Errors versus fitted values. As in how your predicted values increase, your errors should not increase or decrease. Your errors should remain constant. Remember, errors should be having constant variance, so on and so forth. Right? So errors should be constant. So it's more or less constant, this red line, right? It's more or less constant. There is no weird representation. If this red line would have been in this way, in this way, this red line, or if it would have been like that, that means we know for a fact that as and how your fitted values or predicted values increase, your errors are increasing. If it was in this way, if it was in this way, as and how your fitted or predicted values increase, your errors are reducing. So this is fine. Now you need to keep pressing enter, enter. This is called as normal QQ plot, quantile plot. This is used to check whether your errors are normally distributed or not. If all these data points fall along this line, majority of the data points are falling along this line, right? Hence you can say that errors are normally distributed. Here we have errors, residuals are errors. But one key thing that you notice here is 77 and 71. Just remember those, don't worry about those now. Okay, did anyone leave? Oh, Vishal has gone offline. Huh. Now let me enter. I'm also standardizing the errors. I think I have to also explain what is standardization. So I'm standardizing errors for now. Just remember that I'm making it unitless. When we standardize, we are making it unitless. I think yesterday I've discussed during PC, I believe. Standardizing means making values unitless because volume has one unit, horsepower has a different unit, top speed of the car has a different unit, right? And then weight has a different unit. Hence, I'm standardizing and then checking. Here also you have a straight line. That means there is no uh, a trend as such in the data. You have there is no trend in the errors basically. And finally, the last plot, which is called as Cook's distance. Remember from the Cook's distance perspective that if this Cook's distance value is greater than 0.5, that means that observation is influential observation. Assignment for you all. What is the difference between influential observation and outlier? What is the difference between influential observation and outlier? So if you see here, there is one value which is falling beyond 1. So anything greater than 0.5 is influential observation. So 77 is influential observation. What do we do with those influential observations? We need to delete that. Even before we delete that, we are going to check multiple times using multiple plots on whether we can actually delete it or not. So for that, I'm using influence index plot. This is also called as deletion diagnostic plots. If you notice here, this number 77 is standing out when it comes to Cook's distance. Obviously, Cook's distance value, if it is greater than 0.5, that means that observation is influential. When it comes to studentized residuals, you see that 77 is standing out, meaning that is also influential. Bonferroni p-value, hypothesis testing part, right? This value is also turning out to be influential. Anushri and Mamta, I would request you all to also join the hypothesis testing training, which I'm going to conduct for the next batch. I am sorry I did not teach you all about hypothesis testing, right? But we will do so in the next session. Another thing is hat values. Here also you see that this 77th observation is influential, meaning it is standing out. Of course, there is 71 also, but 77 is clearly standing out, meaning that is your influential observation. So let me delete that observation and then construct the model, linear model. When I do that, still this volume and weight are not turning out to be significant. Of course, the R squared value has improved. Earlier it was 77, if you all do not remember. Now it's 81. So removing an influential observation is going to heavily influence your model. If that doesn't do, you'll go with the next influential observation, which happens to be 71. When I look into this deletion diagnostic, 71, 71, 71, and delete that also and check whether the model accuracy is further increasing. No, it hasn't increased. Also, your volume and weight are not turning out to be significant. So the only way around is, let me delete either volume or weight. When I've done variance inflation factor, I've found that weight has the maximum variance inflation factor. So it warrants us to delete that. However, let me do added variable plot. Now look at this plot. We are trying to plot miles given the other values and volume given the other values. And if I do it for miles per gallon and horsepower, miles per gallon and top speed of the car, I clearly know that there is a clear influence of top speed of the car on miles per gallon and horsepower on miles per gallon. However, when it comes to my uh, values, which is volume and weight, these two are not showing uh, a lot of influence. But given these two, I feel that weight is fairly a straight line in comparison to volume. Volume is at least having a slight negative correlation, but here when it comes to miles per gallon, it's more or less a straight line. So this also is saying me that go ahead and delete weight. So we can delete the weight and build a model. That's one thing. Another thing is, if I do not want to directly delete weight, if I want the model to automatically do the things for me, then I'll run this library called mass library, and there is something called a step AIC. AIC stands for archaic information criterion. Why is it not up here now? Ah, it's there. Okay, ASE is used to build when you want to compare the multiple models. Focus, focus, friends. We are done. Focus. Last step. So we have backward step AIC and forward step AIC. If I run this model, all the activities that we have done until now, added variable plot, influential observation, deletion diagnostic plots, and our assumptions plots, and all that, right, is automatically taken care. And look at this. For the first time when it has built the model, it is building the model using all the inputs. And this is your ASC value, archaic information criterion. For the second time, what it is doing is it is removing this first entry, weight. So your AIC, your step AIC is also saying that weight has to be deleted. When we have manually done that, added variable plot was saying delete weight. Your variance inflation factor was telling delete weight. When we do step AIC, it has automatically done that, deleted weight. And it has stopped here saying that, hey, these are the only two models that I can build for you. And the second model has an AAC value of 222.1.92. So we have two models here. One model using all inputs, another model by deleting weight. Both of them have AAC values. So which model do I need to choose? Less or lesser the AAC value, better is the model. Clear? So you'll probably go with this model and say, congrats, we have completed the model.